Hello, good afternoon. I'm Richard Ford. I work for Protean. I recognise some of you from a few conferences around. Today I'm going to talk about in-wheel motors in high-performance cars. So Protean's been very fortunate to be involved with a European OEM on a kind of a low-volume halo high-performance vehicle. We're not allowed to say who it is, but many of you probably know. So that's a very exciting project, and there are some interesting kind of elements to that project which might be of interest to some of you. So as a few bits of introduction, we all know what electric e-axles do, so much cleaner torque response than combustion engines, faster response rate, no gear changes. You can much more easily have distributed drive, and wheel motors kind of take most of those things a step further. So higher bandwidth torque response, less interference with the vehicle package gives you opportunities for vehicle architecture changes, and I'll talk through some of those things today. So I'm sure we all know this, but we don't talk about it. It's kind of the elephant in the room for the automotive industries. There's a lot of kind of uphill struggle going on with the traditional automotive industries. So the governments keep moving the goalposts, as we say in English. Legislation changes are changing the direction that people are moving. Brand loyalty is kind of falling away as vehicles become more and more similar. People are looking at other reasons to buy a vehicle, and this is one of the main ones. So you end up with things like here's the Xiaomi, which really looks very similar to a Taycan, and is a fraction of the price, unfortunately. So there's a lot of challenges facing the industry, and really, when we speak to a lot of people, what they're looking for is opportunities to differentiate. So how can I take my platform and make it different in some way that the customers are going to like and going to actually cause them to buy my product rather than somebody else's? So as a quick intro on what we do, so we've been around for a long time, since about 2008. We've always focused on wheel motors with integrated inverter. So you see all the electronics are packaged on the back of the machine. We're a radial flux outer rotor machine, where the rotor is bolted essentially inside a standard 18-inch or above wheel rim. The only kind of non-standard thing about the corner is the brake disc. So the brake is an inside-out brake disc. The caliper is essentially a standard caliper, but turned around the other way to clamp facing outwards rather than facing inwards. Our current product lineup, we're at Gen 5 at the moment. We've and it's not on this slide, but we've done roughly 10 million kilometers of vehicle durability. We've done all the OEM kind of durability programs, so we're very, very kind of well established and mature. Here's our current generation 5, standard product, 1500 newton meters, 100 kilowatts, 400 volts. We've also, in that family, we've got a separated inverter option. So this is the 400 volt product, but without the inverter. And this is the product that's going into production this year with the OEM that I can't name. And this is a 2,500 newton meter wheel motor, so 5,000 newton meters per axle, 450 kilowatts per axle, 800 volt machine. So let's first of all talk a little bit about mass. This is kind of one of the standard pictures. I'm not very excited about it, to be honest. Kind of mass versus power, and you can see. Well, I mean, as you might expect, the electrically excited are not very power dense, and the PMs are good, and we're kind of over on the good end of that. So we don't have a gearbox, so that helps us quite a lot mass wise. So we think I don't want to claim too much on these because it's easy to argue these numbers, but as well as the machine benefit, there's a lot of benefits in things like subframes and body in white changes that you don't really think about, but they all come along when you don't have to package an e-machine in the middle of the car. I try to include a bit of maths in most of my presentations. So here's a tiny bit of science. For a high-performance vehicle, typically nowadays they're traction limited from 0 to 100k. In other words, your traction control, you would just spin the wheels if you didn't have control. So when traction limited, you've got kind of F equals ma, standard Newton's laws, but that force is essentially, it's always going to be limited by your time u. So you've got F equals ma accelerating force, but the actual traction force is your limit based on your time u. And what that means is that essentially, if you have enough torque in a car, it doesn't really matter what the mass is because it drops out. You're always going to be just given by your time u. And that's one of the bonkers reasons you get these really kind of massive heavy EVs that still do 3.5 seconds 0 to 100 kph. Because if you put a big enough motor in there, it really doesn't matter what the mass is. When you go down to the other end though, you also have to think about the rotating component. So if your vehicle mass is quite light, you do need to think about the rotating components. And then your simple equation here becomes a bit more complicated. You actually have to have a rotating inertia term. And if you have that, that doesn't change the actual tractive force. So there's no extra mass pushing down on the wheels, it's just stopping it accelerating. So that's quite interesting. What it says is if your rotating inertia is significant compared to your kind of mass of the car, you have got to think about that. And so, and kind of another perhaps not obvious thing, wheel motors are heavy relative to not having a wheel motor in the wheel. So let's say the polar moment of inertia of a wheel motor is 1 kilogram meter squared, and let's say I'm comparing it to an e-axle of 0.1. So a much smaller rotor, we're a big outer rotor compared to an e-axle. But we're not geared, so we're direct drive, and a gearbox. This is a number that has been around. A gearbox is roughly 10 to 1 in a central motor. Now the problem is the effective inertia is actually r squared. So you need to think about the gearbox ratio squared. So, and what that means is that for a vehicle, a lightweight, high-performance vehicle, which is traction limited from 0 to 100 kph, it's much better to have wheel motors. So the referred inertia at the wheel of a wheel motor, 2 kilogram meter squared, and of an e-axle, because of this gear ratio, is 5 times as big. And that, you can equate that to mass roughly. It's roughly 50 kilos, 60 kilos more. But the important thing is, when you're down to silly numbers of 0 to 100 kph, it makes a big old difference. So that's almost a 10% difference in 0 to 100 kph time, just because of the difference in rotating inertia. So that's something that most people don't think about. Let's go on to packaging quickly. So I pulled out some pictures yesterday because I thought let's have a look at some EV hypercars versus ICE hypercars, and really, spot the difference. You haven't really got a great deal when you've gone from combustion engine to EV in terms of vehicle packaging, from what I can tell. I mean, maybe it's a bit unfair because there's a whacking great motor and battery stuck behind here, but I don't know. I'm an old guy, so I'd probably rather have one of these ones. So let's think about what happens if you actually choose to put your powertrain in the wheels. So and it really impacts your overall vehicle layout. So here's a traditional vehicle layout. It's an all-wheel drive option, and it's given by your crash structure. So let's have this compressible zone in the front and the rear of the car, and behind that I've got this incompressible lump, which is my motor. And sticking out the side of that, I've got 2 drive shafts. Now that cascade of elements completely defines the wheelbase of the vehicle. So we have crash zone, we have incompressible bit, we have drive shafts sticking out the side. Basically fixes your overhang and your wheelbase, and that also defines the space available for passengers. So when we change this to wheel motor, we kind of break that link. So I've still got the same crumple zone, so exactly the same crash structure in there, but I no longer have this incompressible lump, and I no longer have to connect drive shafts between wheel and motor. So I can put the wheels wherever I want, really. So let's push those as far forward as I want, and as far backwards as I want, and I don't need to have this space for the e-axle in the middle of the vehicle. So that really means that I can have a much more space-efficient footprint on my vehicle. And we see that often. So here's a study that we did a few years ago. There's other presentations about this, but we looked at, I think this is the same footprint as a Passat, roughly. But we said, okay, if I change that vehicle to a wheel motor vehicle, what can I get in terms of interior space, etc. So we pushed the wheelbase as long as we can, and we got two. I don't want to give the whole presentation, but yeah, interior space, fantastic. So we can push the front row bay forwards. Remember, I've still got the same crash structure, so no change in safety, but I've got a much better aerodynamic shape on the front of this vehicle. Staying on the front, I no longer have drive shafts. People know about suspensions. With the suspension, you've got to have kind of a loop round to go around the drive shaft, and then you've got to stack your damper on. If I haven't got that loop, I can lower the whole thing. So I've got a lower hood, even though it's a driven wheel. I've got my longer wheelbase, which I've talked about before. Longer wheelbase, you can package things better, and you can lower the roofline. Lowering the roofline is the easiest way to get aerodynamic benefits out of a car, which nobody really talks about. And aerodynamic benefits are the main reason that you can get efficiency and range out of your EV. Nothing powertrains, forget. Tiny benefits from powertrains. Then your smaller footprint and reduced mass just gives you low overall mass. And one thing I quite like is with a traditional rear-engined machine, you've somehow got to get this diffuser structure. The diffuser doesn't do anything useful apart from kind of release the air to the atmosphere. The good bit is underneath the car. But the diffuser, if I haven't got to get it past drive shafts and an EDU, I can do a much better job of introducing the air back into the airstream. So these are all kind of benefits that you get with on the packaging side when you think about using a wheel motor. So let's think about vehicle dynamics, and this is mostly all to do with the fact that wheel motors are roughly 10 times faster than a central machine. So a central machine, whether you're doing it via drive shafts or by hydraulic actuation, roughly 50 milliseconds from demand to torque delivery at the wheel. With a wheel motor, it's just an electric machine, straight connected to the contact patch essentially, so you're talking about roughly 5 milliseconds, 5 to 10 milliseconds. So you're an order of magnitude faster in your torque control capability. Right, a bit more science, nothing to do with e-machines. In vehicle world, in high-performance vehicle world, when you're driving, you have people talk about a tyre ellipse. And there are a number of regions on the tyre ellipse, whether you're going straight ahead, braking, or cornering. So in the middle is the linear region. Car is very predictable, does exactly what you want it to do, no non-linear behaviour. Then you get to this non-linear region, and in this region, one or more wheels behaves in a non-linear way as the slip heads towards the limit. And then there's a limit of grip, and in the limit of grip, one or both axle has no control anymore. You're sliding. That's the limit at which you have control over your vehicle. People spend a lot of time in torque vectoring world talking about how we alter the limit of grip via understeer oversteer correction. Well, I reckon probably if you're a normal driver, less than 1% of your driving will be in that kind of regime, and probably 10% if you're kind of nearing the limit of grip. So although it might be exciting, you really don't do very much. Actually, almost all of your driving is done in this linear region. If you're talking about high-performance cars, maybe the bias is slightly different. But the good thing is independent wheel motor control can help in all of these regions. They can do interesting things in all of these regions. So let's think about, first of all, the linear region. So in the linear region, I can do whatever I want, really, with these four, if it's four-wheel drive, with these four torques. And if I have a different torque on the left side to the right-hand side, I have a yaw moment on my car. So I have, remember this is 5 millisecond response, I have yaw control over my car roughly with 5 millisecond response time. And this is by far the most impressive demonstrator in our cars. So I think people are used to changing understeer, oversteer characteristics in demonstrator cars, but we take our car. So we have Mercedes demonstrators, not from Munich, and they're quite big cars, but we can really change the feeling of those cars from being a kind of a big heavy Mercedes to a nice small 3 Series. So the key here is it's software defined and configurable. So you can change it and do what you want with it. So and I call this agility modification. So and the example here is if I take like a heavy car and I'm going to turn it into a light car, because if I have a steering input on this heavy car, my yaw moment will kind of be quite slow, and my yaw rate change will be also quite slow. But now I've got control over my yaw moment via the wheel motors. I can change the characteristics here, and I can essentially boost it to make the yaw response much more quick. So a much faster yaw response. So we're not talking about limit control, remember here. This is all sub-limit. So this is all just driving around the streets happily doing your shopping. And so we can make the car feel like a much lighter, shorter, more agile car. So that's what we normally use it for. And I was thinking about this because you might not choose to do that for a high-performance vehicle, and this is getting even more subtle. So in a high-performance vehicle, what you probably want to do actually is to make the car mechanically so that it's very twitchy and fast and responsive. And you do that with the fast steering rack and certain suspension settings. Now the problem is when you do that, you end up with a car that's fantastic on the track, or if you want to have an enthusiastic drive at the weekend, but if your mother gets in the car, or if anybody wants to have a fairly relaxing car, it's not a very pleasant car to drive. So it'll be very twitchy, you'll have to be very focused when you're driving it around the streets. So what you might want to do is do the opposite of what I talked about in the slide before, is take my very sensitive car and calm it down. So we can do the same thing. So rather than kind of increasing the yaw moment on the car, we'll actually work opposite to what the natural behaviour of the car is. This is something else that we've shown. So we're essentially going the other way. So we're starting with a Mini and we're turning it into a Rolls Royce. So we have a very quick, natural yaw response, but we're going to slow it down and turn it into a much slower yaw response. And that's great. We've demonstrated that as well. And so now you've got something where you can say, well, what do I want? If I'm driving a city or at a track, I want a small car. Bigger cars I want for my longer drives or kind of boring daily commutes. Weekend fun, I'll have the small one. And it's all just completely configurable. So that's really quite a powerful tool. It's very easy to calibrate as well. So there's not months of calibration. It's very straightforward. I'll talk briefly. Oh no, I won't. I'll skip ahead because I've got 5 minutes left, I think. Because this is even more complicated. Let's talk about braking briefly. So it's kind of natural to think about, if I've got a powerful motor on the wheel, I'll use it to do as much braking as I can. And one thing I don't talk about here is the nice thing about a wheel motor is the torque reaction happens in exactly the same way as the brake torque reaction. So one of the challenges that you have when you're thinking about transitioning between motors and friction brakes, you need to think about the pitching effect on your vehicle. And if you have different torque reaction paths, when you switch from one mechanism to another, you'll have an attitude change of your vehicle, which is quite unsettling, so you have to be careful. If you have wheel motors, you don't. So there's no change in torque in low reaction path, there's no change in pitching moment. You can switch between the two mechanisms as fast as you want, and the driver won't be able to feel it. And we've demonstrated that. So we've got a very nice brake-by-wire collaborative braking activity function in our vehicles, which does a whole bunch of things. So we make sure we stick within axle limits. We make sure we comply with battery power limits or motor power limits. We make sure we meet all the torque vectoring demands. and then eventually, and wheel slip control, and then eventually we'll split it into motor torque and friction braking torque, where we do as much as we can with the motors, because this is regenning, and then whatever's left over we do with the brakes. And it works really well. So this is just an illustration of how we comply with braking limits. So we do as much regen as we possibly can until we hit that's a battery power limit, and you can see that changing here. So this is the axle balance, and that gives torque demands. So the nice thing about this last one is you see that as the electrical limit gets less, which is this one up here, we blend between motor demand and brake demand to give the same overall demand, and all this happens seamlessly within our controller. So that's really, I mean, it's nothing particular to Protean products. This is really just a wheel motor specific activity. You just need a sensible, intelligent vehicle level controller to do that kind of stuff. And of course you've got higher bandwidth, so you'll have better control. So here's an example of us versus the kind of standard control there, it's a significant difference. I don't really claim that you're going to get that much difference, because there's a whole kind of subjective calibration activity that has to go into ABS. But in ABS world, there's a significant difference. So that's it really. We are about to enter production of the first production vehicle with wheel motors, a high performance vehicle. I hope some of these benefits will be clear in that vehicle. Yeah, that's it from me. I'll take some questions.